Hi, so we're going to start a new chapter. It's chapter 4, and it's on defects or imperfections in solids. So in this chapter, we're going to cover the ideas of how defects are formed when a material solidifies, what kinds of defects are there in solids, can you control the number and types of defects, how do these defects affect the material properties, and are they even undesirable, or are they something that we would actually want to happen sometimes? So in chapter 3, in all those previous lectures, we really just sort of assumed that the order in a crystalline structure was absolutely perfect and there were no defects or irregularities. But real materials, of course, are packed full of defects and lattice irregularities, and they have many, many errors in perfection that have dimensions on the order of an atomic diameter to many lattice sites. So we can classify defects according to their type or geometry, their point defects, line defects, plane defects, and we can also classify them according to how big they are, the dimensions of the defect. One place that defects or imperfections can arise are when a material actually solidifies, when it becomes a solid from the liquid state. So for example, let's say that you're casting a molten metal, okay? So when that happens, you start off with a liquid material, and then what's going to happen is inside the material, there'll be these little nuclei or seed crystals that start the solidification process. Now, where these form could just be from random thermal fluctuations. For example, you have atoms kind of just moving around inside the liquid, and at a certain point, just due to statistical fluctuations, you get a high density region, and that's all it takes to get the process started. Or it could come from impurities inside the molten material itself. If there's some irregularity, something inside there that's already solid, some sort of defect in the liquid, then that can form as a nucleation point as well. But however it happens, you have these little nucleation points throughout the material, and then the crystals start to grow outward from these nucleation sites. So you have solid regions that are growing outward inside this molten material. Now, eventually, they're going to meet up with another region with a neighboring nuclei that's been growing outward. Now, they might not have been perfectly oriented with respect to one another when they form. In fact, it's most likely that they weren't. That this one over here had a crystalline orientation that was tilted this way, and this one's tilted this way, and then eventually when they meet up, you're going to have a boundary where the crystalline structure isn't the same when they meet up. And so that leads to what's called a grain structure in a material. And so you have these grains or domains where the crystalline structure is the same within the domain, but although it might still be, an FCC lattice or whatever, it's rotated with respect to the neighboring grain. And so you're going to have defects present at those boundaries. So you have planar defects that arise when dissimilar crystals meet. So that's one source of defects. If you zoom in at these grain boundaries, then you're going to have these angles of misalignment. And you can see that where the crystalline boundaries meet up, then you've got a lower density right there. Well, that lower density means that in between crystalline grains, the atoms have higher mobility. It's easier to move around when the density is a little bit lower. Because it's easier to move around, they're going to diffuse easier at crystalline boundaries, and also because they're not quite as tightly bound to the atoms at a boundary, these atoms right here at a crystalline grain are not as tightly bound, then they're going to be more chemically reactive. It's going to be easier to get them to chemically react because they're not as tightly bound energetically as their neighbors. So there's a lot of things that can happen at grain boundaries for that reason. So here's an example of an SEM image of some grains that are shown here. Now you can have grains that have kind of a structure where they're columnar or elongated, or they grow in certain directions, or they can be homogeneous or equiaxed, and they're roughly the same in all directions. Here we see one that's definitely elongated along a column, and what happened here was heat was kind of flowing outward in a certain geometry, and that caused the crystals to grow along that axis preferentially. And so you have this really pretty interesting structure that resulted from that sort of non-equilibrium cooling. Now, even without this scenario of the crystalline grain boundaries, there's still no such thing as a perfect crystal, okay? You could have the slowest cooling in the world and have a perfectly homogeneous, defect-free crystal with no boundaries, and you'd still have defects within your crystal. For one thing, you can have vacancies. Vacancies are when a lattice site within a crystalline structure just isn't occupied, and those are unavoidable because of thermodynamics, basically. The entropy just can't be minimized to the point where you don't get these vacancies. Often, however, these vacancies actually help you out, or the defects help you out. For example, in an alloy, a blend of material properties actually improves the material mechanically in many cases. It's desirable. You can also strengthen or harden a material by decreasing the grain size, going through something called strain hardening. And of course, if you decrease your grain size, you've got more grains, you've got more boundaries, you've got more defects. But that changes the material properties oftentimes in a desirable way. So lots of times, defects are your friend if you want a stronger, tougher material. So going over the types of defects or imperfections that you might see, you have vacancies. We already kind of talked about that. That's when an atom site, lattice site, is not occupied by an atom. You have interstitial atoms, and that's when you have atoms that are kind of worming their way into something that's really not a lattice site. And then you have substitutional atoms, and that's when, for example, let's say you're making copper, you might get a little bit of nickel in there too. So that's a substitutional. A nickel atom will occupy a lattice site that a copper atom should be in. So that's a substitutional defect. You can also get dislocations, which are line defects, and grain boundaries, which are area defects, and we'll talk more about those in the next lecture. So point defects, vacancies, basically, you've got these vacant atomic sites in a structure, and what that causes is it causes a strain in the lattice, okay? The neighboring atoms are going to want to bow inward to sort of compensate for that vacancy, okay? So that causes a distortion of the planes. You can also get self-interstitials. So that's when you have, say this is a copper lattice, for example, you have a copper atom that's kind of worming its way in where it's really not wanted. There's not really a lattice site there, but it kind of gets stuck there, okay? And that causes tension in the lattice as well. It causes the lattice lines to bow outward, like is shown here. And so those are extra atoms. So here's a picture that shows a whole bunch of different kinds of possible point defects. There's a self-interstitial. You can see it looks kind of crowded in there. There's a vacancy that we already talked about. Now you can also have impurity atoms in there, like I talked about with the nickel and the copper. Let's say that this is a nickel atom occupying a copper lattice site, okay? And you can get interstitial impurity atoms. Let's say, for example, that this were iron and this is a carbon atom right here, a little carbon atom in the midst of all this iron, and so it can fit into a smaller spot than an iron atom would occupy, and it's an interstitial impurity atom. So the fun thing is that now with today's advanced microscopies, we don't just have to theoretically compute or model these things anymore. We can actually image the defects, point defects directly, which is really, really super awesome, in my opinion. So here are a couple of scanning tunneling microscope images of different metal surfaces. So this is a platinum 111 surface, and you can see the point defects. And these are real images of the surface. So here's some vacancy sites in there. You can see very easily in that beautiful platinum 111 surface. And this is the gorgeous silicon 7x7 reconstruction. So silicon undergoes a phase change at higher temperatures to a different solid form. And you can see in here a number of different kinds of defects. You can, of course, see the vacancies. Those are pretty obvious right away. There's also some things going on with substitutional atoms. You can see that there's something there that probably doesn't belong there, all right? And then you can see some self-interstitials in this image as well. I think there's one right here that you can see. So there's defects that can be seen directly in scanning tunneling microscope images. Now the fun thing is that you can also take movies. So if you want to, you can take a series of STM images of a surface once you get your atomic structure, and you can watch these defects move around, make a little film. So that's fun. This is a transmission electron microscope image. For transmission electron microscopes, remember you have to make thin sections and shoot it through. These guys were actually controlling the number of defects in graphene at the nanoscale by irradiating it with the electron beam. So they took a quick picture, and you can see this beautiful, pristine image of the graphene, and then they irradiated it for varying lengths of time and continued to take images of the surface. And you can see that after they irradiated a little bit, they created one vacancy, they irradiated more, they created more, and it changes the lattice structure as they show here in this cartoon down here as they irradiate it more and create more vacancies. And then here is an aberration-corrected transmission electron microscope image of a single layer of graphene oxide. And you can see here they've taken the raw image and then they've color-coded it to show the types of defects. So blue regions are one kind of defect, disordered single-layer carbon networks. Red areas are individual add atoms or substitutions. Green areas are isolated topological defects like bond rotations or dislocation cores. And holes in their edge are in yellow. So you can see they color-coded it for the type of defect, which is kind of fun. And then finally, just one more, because of course this is my thing and I'm super excited about it always. But anyway, this is a scanning transmission electron microscope image of some silicon nanowires, and what they show here is substitutional defects, substitutional interstitial atoms. So within the silicon nanowire, you can see these little gold atoms that are cropping up where they're not supposed to be. Okay, so that's kind of fun too. All right, I promise, that's all. Now, the equilibrium concentration of the number of point defects varies according to the temperature. And so this is the relationship here. Here we have the number of vacancies divided by the total number of atomic sites. So that's NV over N. That creates a little fraction of the total number of defects in the sample. So you have a fraction that's established there. And it's got an exponential dependence. So here we have e to the minus QV over KT. QV is the activation energy, which is the amount of energy that it takes to create that vacancy in the first place, to dislodge the atom from its site, okay? And that's usually a fraction of an electron volt in energy. K is Boltzmann's constant. It's the sort of thermodynamic constant, 1.38 times 10 to the minus 23 joules per Kelvin, or 8.62 times 10 to the minus 5 EV per Kelvin. Pick your poison there. And T is the temperature in Kelvin, okay? So that's the formula dictating the number of concentration of defects. And we can get the activation energy from an experiment. For example, if you have a material and you vary the temperature of that material and you measure the number of defects or the fraction of defects, then you can get an exponential dependence. So here, as we increase the temperature, we see this exponential curve forming right here. And then you can take the log of both sides, and that forms a straight line. And from the slope, you can extract that activation energy. Okay? So if you want to do that, you can. So the example that I'd like to show here is for estimating vacancy concentration. So this one says, find the fraction of sites that are vacancies in lead at 327 Celsius, which is 600 Kelvin. The givens are the density of lead, which is 11.35 grams per cubic centimeter, the atomic weight of lead, which is 207.2 grams per mole, the activation energy for creating a vacancy, which is 0.55 electron volts per vacancy created, and then, of course, Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. So those are our givens. We're going to use our formula and say that the fraction of vacancies is equal to the number of vacancies divided by the total number of sites, NV over N, and then that's equal to e to the minus QV over KT. So if you plug in for QV, you get e to the minus 0.55 EV divided by Boltzmann's constant, 8.62 times 10 to the minus 5 times the temperature. And then you get the fraction is 2.41 times 10 to the minus 5. All right. Now, in 1 cubic centimeter of the material, how many defects would this correspond to? Okay. So in order to get the number of defects, you multiply your fraction times the total number of atoms in the lattice. So here, the total number of atoms in the lattice would be the fraction 2.41 times 10 to the minus 5 times Avogadro's number, 6.022 times 10 to the 23rd atoms per mole, times the density, 11.35 grams per cubic centimeter, and then divided by the atomic weight, 207.2 grams per mole. And when you do that, then you get the number of total sites N multiplied times that fraction is 7.94 times 10 to the 17th vacancies. So in 1 cubic centimeter of a material, then you have 7.9 times 10 to the 17th defects. All right, so in case you were thinking that the number of defects in a crystalline material is small, it's not, okay? Materials are just absolutely chock full of defects, and they only get larger as the temperature increases. Now, this is a fun thing that got shown. Okay, I said I was done, but I'm not really done. This is reprinted with permission from Nature, and what they've done here is they've taken an electron microscope view of a surface. So what you can see here are these little atomic terraces, okay? So before I press play on the movie, what you're seeing is a plane sitting on top of another plane, sitting on top of another plane, okay? So you see boom, boom, boom. Okay, now what happens is they change the temperature and then took movies of what happens to the surface over time. If you increase the temperature, of course, that causes the number of defects to increase. But where do those atoms go? What happens is it increases the volume of the material, right? If you have more vacancies, then the volume of the material goes up, which means that atoms from, say, a layer underneath have to hop up to the next terrace. And so you can watch the size of the terraces grow and shrink as it changes the temperature of the material. So watch this. So here the temperature is increasing. You can see the islands expanding, and then as the temperature decreases, the islands contract. And that's just because the atoms are hopping up from underneath as they're kicked out and the vacancies are created, and the volume of the material actually has to expand as the temperature is increased. Okay, so that kind of gives you a whole new take on that thermodynamics that you learned in physics 1150, 1151, right? We all know that the size or volume of materials increase as the temperature increases, but now we've got firsthand evidence as to part of the reason for why the vacancy is increasing. Okay, of course you can also get the size of the bonds themselves increasing as the temperature increases, but this is not an insignificant contributor to the idea of volume increasing with increase in temperature. All right, I hope you enjoyed that. We'll continue on in the next lecture with a discussion of line and plane defects.